There are three things that I want you to get out of this talk, and I think you can handle it. One, magnetic fields are important. Two, they are difficult to study. And three, computers can help. Now, magnetic fields are everywhere. They make your compass wiggle, they make stuff stick to your fridge. There are little ones, medium ones, and there are big ones. How big? Well, think of the biggest thing you can think of. Okay, it's even bigger than that. And to give you a sense of the scale, I have a little movie for you. This movie is going to start from our local group of galaxies. So we're already outside of our Milky Way galaxy and in our neighborhood. And we're going to start zooming out. And as we fly through and see all these galaxies, the large-scale structure of the universe begins to emerge. Now, this is not from a simulation. This is actual data from the Sloan Digital Sky Survey. So these are real galaxies with their real positions. And you begin to see the beginnings of this web-like structure, this structure of filaments and voids in the universe. Everywhere where you see glowing stuff, there are magnetic fields. And the structures that we're going to look at are called clusters of galaxies. These are the largest gravitationally bound structures in the universe. They exist at the intersections of these filaments. And that's what we're going to look at. And by the way, this cone here, that's the edge of the survey, not the edge of the universe, in case you were wondering. Now, magnetic fields play a lot of roles in clusters. For example, if two clusters merge, we'll stop it there. If two clusters merge, all that energy gets released as turbulence. And that turbulence can accelerate cosmic rays, which are tiny charged particles. These cosmic rays spiral around magnetic field lines and emit radio waves. So if we take a radio telescope and look at a recently merged cluster, we can see what are called radio halos. In these plots, you're seeing maps of radio intensity contours overlaid on an X-ray image of a cluster. Now, these radio halos are highly sensitive to the properties of the underlying magnetic fields. We performed a large-scale simulation to study this sensitivity, and we found that if you're going to take the next generation of radio telescopes, so the telescopes that are being built right now that are sensitive in a certain range, and will be observing at a certain set of frequencies, they can see up to a factor of 2 difference in the total number of radio halos in the universe, depending on the strength of the underlying magnetic field. So even though in these magnetic field strengths, this difference is very, very small, but this is just one example of the power of these magnetic fields. So why are they difficult to study? They're difficult to study because of the extreme range of scales involved, and because we don't really understand where these large-scale fields come from. There are a lot of stories out there, and here's one particular scenario that we're going to follow in simulation and examine in more detail. In this scenario, you start off with a completely unmagnetized universe. And there's a few relatively benign astrophysical processes, like the Biermann battery mechanism, you can look it up, that can magnetize an initially unmagnetized plasma. So this gives you a very weak seed field, but it's much weaker than what we observe. You need some mechanism to amplify that field up to the observed value. And for that, we turn to dynamos. There's a dynamo in the Earth's core that's responsible for our magnetic field, and there are plenty of other dynamo sources out there in the universe, such as the accretion disks of active galactic nuclei. We're going to talk about AGN more in a little bit. So this gives you the observed strength of magnetic field, but they're confined to this very tiny accretion disk system. We have to get these fields out all the way out to fill up clusters of galaxies. And AGN can do that too through ejected jets and bubbles. And then you can get some further processing from structure formation, merger, turbulence, things like that. So what are active galactic nuclei? What ingredients do you need to make an AGN? Well, here's a radio image of a real AGN, and this is to help you get through the rest of the talk. To make an AGN, you start off with a supermassive black hole. This is a black hole that is at least 1 million times the mass of the sun. So we have one of these in the center of our Milky Way galaxy, and we believe that there's one in the center of every single galaxy. Gas can accrete onto the black hole. As it accretes, it flattens to form an accretion disk. Dynamo action in that accretion disk can amplify a weak magnetic field. Then that magnetic field launches and collimates a bipolar jet that extends tens of thousands of light years, all the way outside of the galaxy, all the way into the cluster medium. These jets then form these bubbles. They inflate these very large bubbles, which detach, rise up into the cluster medium, and disperse, distributing heat, energy, and potentially magnetic fields. To give you a sense of scale, our entire solar system is smaller than this dot, the red dot of the laser pointer. So this is the scenario that we want to test in simulation. We want to see if AGN are responsible for the large-scale magnetic fields in clusters. So to do that, we need computers to study this. We have a couple requirements. We need relatively large volumes. We need to simulate a lot of clusters so we can get good statistics. We need relatively high resolution in order to capture the nature of the magnetic field. But even with our most powerful resources available, we can't simultaneously follow the evolution of the universe and these very small accretion disk systems. So we turn to what are called subgrid or sub-resolution models. These are essentially toys that we carry around in our simulation that mimic what we observe in nature. Now, the typical strategy for involving these subgrid models, especially AGN subgrid models in simulations, is to pick some model of accretion and feedback, some model of carrying around your supermassive black holes, allowing them to merge in your simulation. You shove them into some large-scale run, you get results, and you compare against observations, and you get the wrong answer. But fortunately, there are enough tunable parameters in these subgrid models. Some are more physically motivated than others. And you start tuning them and tweaking them and going on this cycle over and over and over again until you are able to match observations, and then you write a paper. So this is exactly what happens. So we want to offer a more robust approach. We want to be as careful and systematic as possible. So what we did is to independently study and evaluate models of accretion and feedback, then independently study and evaluate models of black hole seeding and merging before placing them in our large-scale simulation. Then when we get results at the end of the simulation, we can be as robust as possible in making our predictions, and if we can't match observations, then we can confidently say that this model fails, that we can't explain large-scale fields. And if we can match observations, then we can confidently say that we have the right model. That's just not a numerical toy effect, that we're actually trying to match the real physics. To give you an example of the kind of subgrid model study we did, I have another movie for you. So how many of you were at SIDAC the other week? Okay, if you were there, you've already seen this movie at the Viz Night made by Dave Pugmire at Oak Ridge. It actually won a couple awards. In fact, Dave just emailed me this morning saying that Wired Magazine is going to do a write-up about this Viz. It's no Dixis, but we'll take what we can get. So what we did for this study is to take an isolated galaxy cluster and stick an active galactic nuclei in the middle. And we test different subgrid models of applying that jet and bubble system into the cluster. We allow it to spew magnetic fields out for about 6 billion years. That's billion with a B. And what you're going to see are the magnetic field lines for each of these cases. So our first model that we're going to study are the jets. We're going to attempt to simulate those thin bipolar jets. And what you're going to see are the magnetic field lines produced by those jets. This is colored on gas density of the cluster, so this is the middle of the cluster. You see that we get a very regular dipole-like pattern in the magnetic field. This is not what we observe in real clusters. Real clusters have a very complex, tangled topology of the magnetic field. So with jets, we're able to get the correct strength of fields, but not the correct structure. So next we turn to bubbles. We skip modeling the jet and just place random sporadic bubbles near the black hole. And in this case, as you can see, we very naturally get very tangled fields, more like what we see in real clusters. This is because the bubbles are overlapping each other and gas is falling in, there's lots of turbulence. But in this case, we do not match the observed strength of magnetic fields. We get about a factor of 10 less than what we observe. So what we go to next is kind of a Goldilocks solution, a middle ground between the models that we call fixed bubbles. In this case, we still have sporadic random bubbles, but their location is centered on the black hole, and they're allowed to naturally rise up into the cluster medium. And in this case, we do get naturally tangled magnetic fields, like how we observe in nature, and we're able to match the observed strength of magnetic fields. So this is the model that we choose for our large-scale simulation. And this is what we put into our subgrid model. Isn't that pretty? And just as a side note, we're not just playing games with these visualizations. These streamlines appear in our paper, and so we're doing science with visualizations, which is always an exciting thing to do. Now, this large-scale run, here is the complete listing of all the parameters used in our subgrid model. This is a much longer table than you'll see in some other works, because we wanted to fully specify our model and test each and every single one of these parameters. Now, this simulation that we plug this model into is so expensive, it's actually still running right now. It's going to cost about 20 to 30 million CPU hour for a single run, which is why we wanted to be so careful. So it's still running now, so we don't know yet what our results will be. We don't know yet if AGN are responsible for large-scale magnetic fields. But we do know that the results that we will get will be as robust as possible, which was the goal. So what have we learned? Magnetic fields are important, they are difficult to study, and computers can help if you're careful. So this is the usual list of people I'd like to thank, and I'd like to thank you.